Hello, welcome back to our video lecture series for functional programming. In this video I want to introduce a little bit of how we can use functions to produce abstraction. So where we finished off last time was we had a function to take the sum of a list and a function to take a product of a list. And you can see that these functions are remarkably similar. I know in many ways so is this list length. They all start off with an if that checks if the list is null. If it is, they return some base case 0, 0, or 1. Otherwise, they do something with both of these have a function that's applied to the car and then the recursive call on the cdr. This one's a little bit different. It doesn't do anything with the car actually. It just returns, it adds 1 to the recursive call on the cdr. And so what I want to do is figure out how we can simplify these, definitely to make these two the same. And it turns out that once we write a single function that can do these two, it's really not hard to make it so that it can do this one as well. So obviously we're going to start off here by copying and pasting this, and I'm going to call it reduce list. Okay, so we want to have some way of dealing with the things that are variable in here. So what were the things that varied from one of these to the other? Well, one of them was the base case. Either you return 0 at the bottom or you return 1 at the bottom. And so in addition to passing in a list, I'm going to pass in a value called base. And I'm going to make it so that when we get down to the bottom, we return base, whatever it is. The other thing that differed was the operation that was passed in here. And this is where the power of functional programming comes in. This is something that in most imperative languages would be very hard to do, to basically to pass in a function. And what I want to do here is I want to pass in multiply or pass in plus. Those don't communicate. That's a concept that does not communicate very well in most imperative languages. But fortunately, we're not in an imperative language, we're in a functional language. And so I'm just going to say there's another argument here called f, and I'm going to replace the star with f. If I save this and run, we can see how close we're getting. Reduce list. The list I'm going to do, let's say I'll do this first with, there's our list. If I do it with addition, I pass in 0, and the question is, well, what should f be? Well, f is simply the plus. Okay, so where is the error? I still have this reduced list, and all it's taking is the cdr of the list, and now we need to also pass through base and f. It's worth noting that in a lot of those languages where I would have a hard time expressing f, this would have been caught at compile time. So when I hit save and then, oops, and the Control T to run, that error would have been caught. We'll also see that there are other functional languages where that error would be caught. But Scheme has a lot of flexibility, but part of that flexibility is that it does not necessarily check for you in advance that you're passing the right number of arguments into a function. Okay, so 1 plus 2 plus 3 plus 4, yep indeed, that's 10. Now, the argument is that this is more powerful because I don't have to do this with plus. If I pass in a 1 for the base and multiplication, I should get the product of that list, which is 24. Okay. How would I get the length of the list? Okay. So we know from up above where we had our function calculate length that the base is 0. But now we need some function that is going to, so first off, it has to be a function that takes two arguments. It takes the car and it takes the application onto the cdr. And whereas plus and star had very nice names, they were already predefined for us, they were already part of the scheme language, the function I want here is not part of the scheme language, so I have to create my own function. Well, remember that's what lambdas are for. Now this lambda needs to take two things. First I'll just type them in as x and y, and then a body. This is not what I will change these things. What is x? Well, this is a single element, and this is the compiled result so far. In this case, so actually it's worth noting, just so that we can make this clear, what happens if I do plus elem result? And what is that going to do? 10. That number should look familiar to you. That's the same number that's up here. Because this lambda was really just a lambda that takes x and y and returns the plus of x and y. This would have been a redefinition of plus on two arguments. And so if I use that, it darn well better do addition. But that's not what I want here. Okay. If I just want the length of the list, I want to add 1 to the result. And because in reality, the length doesn't care about the individual elements. And sure enough, that list has a length of 4. What else could we do? What if I made it so that, now this one is going to, okay, well, we could do this. They're all numbers. Actually, we can, let's first do this the simple way. I want to make it so the base case, I want to return something that is a list. There's my base case. And when I get a new element and the result so far, what I want to return is the cons of the elem onto result. And so you should look at that for a second. Think about what is that going to give you. Feel free to pause the video as you think about this. When it gets all the way to the end of the list, it's just going to return a null. And then as it pops back up the call stack, it is going to take each element and cons it onto the result. So we're going to have null, and then we're going to cons on an element. And remember, this is popping back up, so it will cons on the 4. And then it will pop back up another level, and it will cons the 3 onto the list with 4. And then it will cons the 2 onto the list of 3, 4, etc. And hopefully you can see that that gives us back our original list. Okay, well that wasn't all that interesting. What if I wanted back a list where the elements had all been multiplied by 2? Well, that's at least a little bit more interesting there, because it doesn't look like I've just recreated the same list. No, I didn't. I actually built a new one, which, because schemes lists are immutable, was a rather wasteful thing to do, but it demonstrates that I have the power to do it. So this one function right here, because we have abstracted it, because we've made it so that we can pass in these additional arguments, is a much more powerful function than the things that we had written above. It really has the ability to go much, much further and to do a lot more than what we had done before. But because of the ease of passing in functions such as addition and multiply, it can also recreate some of this functionality that we had before very simply. So take some time to think about this. Maybe see what else you can do with the reduced list function, what types of things you can make it calculate. Interesting. Yeah, I'll let you think about that for a while. And we'll come back later and we'll write some more code.